We are now moving on to calculating probabilities that involve the word or. So we're still using a similar example that we saw in the last couple videos, and that is we're going to roll a six-sided die and flip a coin. We're doing this at the same time. We want to know what's the probability of getting a result containing an even number or a 5. When you see that word or, and you think about or statements, think about addition. Think about adding. Or is associated with the addition rule. And we're going to get to the formula for the addition rule. But the first thing we want to consider before we move on to actually calculating it two different ways is whether or not these two outcomes, getting an even number and getting a 5, are they disjoint? If they are disjoint, and another way you will hear the word disjoint is whether or not they are mutually exclusive. Think about, is it possible for both of them to occur at one time? So if you think about all of the outcomes, and notice I've already gone down here and listed the sample space, tails 1 through 6 and heads 1 through 6. These are all the elements of the sample space. Is it possible that both of these two events, if we call an even number, we're going to call that event A, and we'll call getting a 5 event B, can they both occur at the same time? If you notice, if you get an even number, that's T2, H2, T4, if you get an even number, you're not going to get a 5. So we would say that these are disjoint, and that is they can't both happen at the same time. You either get an even number or you could also get a 5, but they can't both happen at the same time. So these are called disjoint events. They are also called mutually exclusive. So for that reason, we're going to be working with these two situations. The formula method's actually going to change. But first, let's just look at the sample space. The sample space method, remember, we are going to calculate the probability of getting, let's say, an even number, or a 5. So one thing that we could do is to just go through and count all the outcomes that are favorable. So it's either even or it's 5. We don't care if it's even or if it's 5. We just want to make sure it's one or the other. So if I go and underline, I have T2, H2, those are both even. T4, H4 are even. 6, both 6s. And those satisfy the even part. And here, this is 5 and 5. It doesn't matter if it's even or it's 5 as long as it satisfies one of those. So if I count that up, 1, 2, 3, 4, 5, 6, 7, 8, there are 8 favorable outcomes where our event will be satisfied here. Out of a total of, as we calculated in our last examples, there are 12 possibilities. So if you put that into your calculator, what you're going to get with 8 divided by 12, you're going to get, if you simplify this, you'll get 2/3, which is approximately 0.67. You have a probability of 0.67 of getting an even number or a 5. What I did there was just add up all the even number outcomes and add up all the 5 outcomes, those outcomes that have a 5 and those outcomes that have a 6. So if you have the sample space written out, this is a great way to do the problem. The other way that you can do this is using the formula method. And if you know that two events are disjoint, or if you know, in other words, that these two events are mutually exclusive, and I'm going to abbreviate that. Those are the same thing. They're either disjoint, two things are disjoint, they're also mutually exclusive, then we can use this formula. The probability of A or B, which we also will see as the probability of A union B, or when you think about union, it's an or. This will be equal to the probability of A plus the probability of B. And notice this is only for disjoint or mutually exclusive probabilities here, mutually exclusive events. So if we know that there's no overlap between them, then I can just find each one separately and add them together. So that means if I'm looking for the probability of even or the probability that I get a 5, I know they are mutually exclusive. So that means I can find each one separately. and add them together. So the probability that it's even, I get an even number, or the probability that I get a 5. So I can find each one of these separately. So the probability of getting an even number is 1, 2, 3, 4, 5, 6. There are six possible outcomes that are favorable to being even, divided by 12, the total number of outcomes. The probability of getting a 5, there are 2 outcomes out of 12. So if you take this is 0.5 plus this is approximately 0.17, you're going to get 0.67. If you have the sample space written out, you can just kind of follow through with what we did the last couple times. If you don't, then you can add the probabilities. The key here is knowing that these two events are mutually exclusive. You can find each one separately. On the next page here, we're going to look at whether or not, or we're going to look at an example where two events are not mutually exclusive. So let's check that out. Now we're looking at a similar situation. What's the probability of getting a result? Now we're looking for a tails or 4. So we could get a tails or a 4. So remember, with the sample space method, we can just look at the sample space, which I already have written out here, and just underline the outcomes that are favorable. Either we get a tails. So anything that has a tails is going to be good. So I'm going to go ahead and underline all the ones that have tails because those are favorable. Or a 4. Now we're going to underline anything that has a 4. Well, it looks like the tails and the 4 is already underlined, so this one has a 4. And those are the outcomes that are favorable. Those would satisfy this requirement of having a tails or a 4. So if I count these up, I see that I'm going to have 1, 2, 3, 4, 5, 6, 7. I have 7 favorable outcomes out of, remember the sample space, there were 12. So my probability is 7 out of 12. And if I pick up my calculator here, 7 divided by 12, this is going to be approximately 0.58. Okay, so again, just counting all of the favorable outcomes dividing by the total. Now let's look at this. Are these outcomes disjoint or mutually exclusive? In the last example, we looked at an example where they were, right? There were 2 events that couldn't occur at the same time. Now we have 2 events, getting a tails and getting a 4, and we want to know, are they mutually exclusive or disjoint? Can they occur at the same time? If you look at our sample space, it's pretty obvious that they can. All right, we can have both of these events occurring at the same time. So what we would say is these are non-mutually exclusive events. The key here, and what's going to make this different, is if they were mutually exclusive, just like our last example, then using the formula, we could just figure out the probability of getting a tails, and then adding the probability of getting a 4, and adding them together. Now, let's just do that real quick, and without, if we assumed they were mutually exclusive. The probability of getting a tails is 1/2, or 6 over 12. And the probability of getting a 4 is 2 out of 12. So if I added that up, I would get approximately 0.67. Now what's different? And that's wrong, right? This is not what we got up above. Why is this formula for mutually exclusive giving us a different answer than the sample space method? The reason why is because when we add 6/12 and we add 2/12, we are double counting. We are double counting this tails and 4. If you can see that. When we add up all the tails, there are 6. When we add up all the ones that are 4, there are 2. The issue there is we are counting T4, tails and 4, 2 different times. So if 2 events are non-mutually exclusive, what we need to do is we need to take the probability that the first event happens, we'll add that to the probability that the second event, but we need to remember to subtract out the probability that A and B both happen. So A and B. So in this example, if we're looking for the probability that we get a tails or a 4, we can add up the probability of getting tails plus the probability of getting a 4, But then we need to subtract out the probability that we have a tails and 4, where they both occur at the same time, because this is going to be double counted. When we add tails and 4, this is going to double count because both of these things, the tails and the 4, occur in both of these events or both of these probabilities. If you notice, this formula could have worked as well in the previous example, but this probability would be 0. The probability of tails, and in the last example, we had what's the probability of getting an even number or a 5? Well, the probability of these two things both occurring would be 0. So that's why this just canceled out. We would be subtracting 0. So now let's look at the formula approach. The probability of getting a tails, there are 6 outcomes that are favorable, so 6 out of 12. The probability of getting 4, there are 2 favorable outcomes, so 2 out of 12. And then we need to subtract the probability that they both occur. The only one is right here, tails and a 4. That's the only time that they both occur. So if you were to add all these up, you would get approximately, this would be 1/2. Oh, actually, you can just add up all the numerators here, and you'll get 0.58, the same answer. You'll get 6 plus 2 is 8. 8 minus 1 is 7/12. Again, this is different than the last example because the last example we had 2 events that were mutually exclusive. They both couldn't occur at the same time. So we didn't have to worry about overlapping or double counting events or double counting outcomes, if you will. But in this example, when we add the probability of event A, which is getting a tails, to the probability of getting a 4, which would be event B, when we add those, we're actually double counting a one outcome in particular. So we need to subtract that out. Subtract out that one, or potentially more. In this case, it was one outcome where they double or overlap, where they double count or overlap. So the first question you should ask yourself when you're looking at an OR statement and you're asked to find the probability of an OR statement, are they mutually exclusive? If they are, then go ahead and just add their probabilities. If they're non-mutually exclusive, then you can add their probabilities, but you need to subtract out that common ground, the one where they both occur.